For many years, the forests of eastern Canada have been threatened with destruction by an insect called the Spruce Budworm. This film will attempt to describe an aerial spraying project that has been carried out each year for the past 23 years, except for 1959, to prevent massive damage and to conserve the province's most important natural resource, the fir spruce forest. The budworm in its life cycle lives through 4 stages: the egg, larva, pupa, and moth. There are 6 phases to the larval stage. These are known as instars. It overwinters as a second instar larva in the flower cups or other protected spots on the trees. It's very small and barely visible to the naked eye. When warm weather comes in early May, it becomes active and starts feeding on old needles and new buds. It grows larger in each larval instar. As it gets bigger, so does its appetite. Consequently, an attempt is made to spray it in the 3rd, 4th, and 5th instars when it's big enough to be readily contacted by poison, but before it has eaten off all foliage. In late June, the budworm pupates for a couple of weeks and emerges as a moth. The moth breeds, lays eggs, and dies, all within a short period of a few weeks. The eggs hatch in late July and early August, and the very small larvae locate a place to overwinter. The cycle starts all over again the following spring. There's only one cycle per year. Areas considered for spraying are determined by a number of factors, such as number of bugs or budworm egg masses, tree condition, previous damage, current defoliation, forest susceptibility, and other observations backed up from several surveys conducted by Forest Protection Limited of New Brunswick and the Canadian Forestry Service of the federal government. All of these factors are weighted at 1,200 locations throughout the province, combined with results from the aerial survey for defoliation, and then a tree hazard story evolves. If it's felt that the hazard is enough to cause tree mortality, top killing, or severe growth reduction, the area is included in the plan regardless of who is the owner. An important factor in defining hazard is the egg mass population of the spruce budworm. Egg infestations are categorized as follows: 0 to 99 egg mass per 100 square feet of foliage, light; 100 to 239 egg mass per 100 square feet of foliage, moderate; 240 to 399, severe; and 400 plus, extreme. The latter category indicates a population of bugs that will destroy 100% of the new foliage plus some old foliage. A map of the areas to be sprayed is derived from this information. Each black square, shown here, represents 12,500 acres of forest, and it's the workload for one team of spray aircraft. The aerial spray operation is carried out each spring from several small bush airstrips located at such places as Chipman, Juniper, Upper Blackville, Sussex, and Blissville, New Brunswick. The most efficient spray aircraft to this date for this type of work has been the Grumman Avenger, a World War II torpedo bomber. It's one of the only single-engine aircraft with the speed, range, and load-carrying capabilities necessary to handle the operation economically. It's powered by a 1900 horsepower engine, and for this work carries 625 gallons of spray mixture. Each spray area, or 12,500 acre block, is sprayed by a team of 3 Avengers. Because these aircraft must fly at an altitude not higher than 150 feet above the trees at any part of the block, becomes very difficult to precisely navigate over the forest. Smaller Cessna aircraft are used for pointing or navigational purposes. Each Cessna carries a crew of 2, a navigator and a pilot. Each Avenger team is led over the spray area by 2 aircraft or a pointer team in a manner which will be described shortly. The chemical used for the project is called phenitrathion. It's an organophosphate poison and is sold under numerous trade names such as volathion, acathion, sumathion, novathion, and some others. The technical or concentrate poison is made into an emulsifiable concentrate or EC with the addition of Aerotex oil solvent and an emulsifying agent such as Atlox or Toxamol. To formulate the EC, raw phenitrathion is drawn from 45-gallon drums and transferred to a mixing machine. A rough weight formula for the emulsifiable concentrate is 78% technical phenitrathion with 11% solvent oil and 11% emulsifier. This is mixed and as such is stable. The EC is mixed with water, 9 parts water to 1 part EC, to make the emulsion just prior to entering the airplane. The mixture is pumped from several mixing machines to the airplane. A metered valve regulates the amount being pumped and ensures that no more than the required 625 gallons enters the plane's tank. During spraying, another configuration of pumps and plumbing transfers the mixture from the spray tank through several flat fan spray nozzles. No one is certain as to the exact size range of the droplets being emitted from the nozzles, but they are generally small, or less than 100 microns. A study of the spray cloud was undertaken last year by the Chemical Control Research Institute and will be continued for several years to come. It's a very difficult study, however, because the water portion of the droplet evaporates depending on the relative humidity of the air. The spray company claims that with the spray equipment being used at an aircraft speed of 156 miles per hour, the droplets coming out of the nozzle should be around 100 microns. There is little point in striving for proper mixture ratios and emission rates, of course, unless we ensure that the emulsion is applied to the forest in such a way that the exact dosage lands on the trees. The 1971 areas of the spray program, which were to receive 1 application, received a dosage rate of 3 ounces of active ingredient applied at the rate of 0.15 U.S. gallons of formulation per acre. In areas of the plan receiving 2 applications, each coat contained 2 ounces of active ingredient at the same application rate, 0.15 U.S. gallons per acre. A simple yet very accurate navigational technique is employed. Assume that we want to spray Block 523 in the Juniper area. The pointer plane's navigator will use a 1 to 500,000 scale, or approximately 1 inch to 8 mile map to direct his pilot to the spray area. However, such a map lacks considerable detail. Therefore, as he approaches the block, the navigator will need additional, more detailed information from a map of the scale 1 to 50,000, or approximately 1 inch to 4/5 of a mile. These maps clearly show swamps, footpaths, creeks, and contours, which are vital aids and enhance the precision which is necessary in the navigation. To ensure that the exact amount of spray falls on each acre in the forest, that no part of the block is left unsprayed, and that no part of the block receives an overdose of spray, it's necessary that the spray planes are guided over the trees in a grid pattern. Each pass or swath across the block by the 3 spray aircraft must be 1,000 feet wide. The navigator will apply a grid representing the swaths to be flown to his 1 to 50,000 map. The starting corner and direction of flight movement across the block are determined by two factors: the proximity to the airstrip and the wind direction. In the case of Block 523, the Juniper airstrip is closest to the northern end. Assuming that there is a very light wind from the east, we would then start in the northwest corner of the block and move eastward. It's essential that the spray aircraft turn away from the spray at the end of the block. If the air is very stable, it's not unusual for the spray swath to remain suspended in the air for several moments. If the swath happened to drift somewhat, say toward the aircraft during their next pass in the opposite direction, the combination of the two suspended swaths would result in an overdose falling on the trees. Flying the aircraft through a suspended swath would also reduce visibility for the pilot and may in fact have nauseous effects on him. As mentioned, the spray aircraft are led by two pointer aircraft over the block. Prior to a spray session, or just before taking off, the pointer crews may discuss particular aspects of the blocks to be sprayed during that session and any other particular procedures to be carried out. The pointers will fly out to their first block, examine it, and familiarize themselves with it, and call for the spray team when they are ready for them. In the meantime, the spray aircraft are loaded with the emulsion. The spray pilots, when called, will navigate for themselves using a 1 to 500,000 scale map as far as the spray block area and until they sight the pointer aircraft. From that time until they have completed the block, the navigation becomes the concern of the pointer aircraft. As the first pointer aircraft arrives at the northwest corner of Block 523 and circles, the second pointer aircraft circles at a point 2 to 3 miles north of the block in line with the first swath line. The spray aircraft will approach from the northwest. They will inform the pointers when they have them in sight, and when they are lining up and ready to start down the first line. They'll be flying at 156 miles an hour. The pointer aircraft will fly at about 80 miles an hour. By the time the spray aircraft reach the northwest corner of the block, the number 2 pointer aircraft should be directly above them and will inform them to begin spraying. The first pointer aircraft should be about halfway down the line at this time, and the spray planes will follow it to the south end. The spray aircraft and the first pointer airplane should reach the south end of the block at the same time. The first pointer will tell them to stop spraying, or say booms off, and turn left, and continue up the next line. They will spray northward on the second line, and the second pointer plane will be directly above them at the shutoff point. At this point, the second pointer will call booms off and direct the sprayers down the third swath. Each spray aircraft must be separated from the aircraft next to it by 8 wingspans. It's up to the navigator in the pointer airplane to adjust that separation. Each spray swath is timed and should be 2.5 minutes in length. Total time per 12-line block is checked to ensure that the proper speeds are being used and that proper calibration is used. Ideal spraying conditions exist in the very early morning or in the evening. Usually at these times, the temperature is low in comparison to day temperatures and the air mass is generally stable. As a result, the spray readily falls to the trees and there is very little wind to cause any severe drift problems. Later in the day, say after 9:30 in the morning, the temperature increases. The warm air near the ground tends to rise and becomes unstable. Wind develops and the spray no longer falls directly onto the forest. It may in fact rise. Naturally, an ideal time to spray exists at the approach of a warm front. That is, at the transition zone between warm and cold air masses, where the warm air overrides the cold. In this situation, the air is very stable as there is an inversion. The air at the higher altitude is warmer than that near the ground, so there will be no tendency for the air at the ground to rise. The approach of a warm front, however, is characterized by decreasing visibility, lowering cloud ceilings, and precipitation from a steady rain. Flying then becomes hazardous. The days are few and far between when spraying may be carried out into the middle of the afternoon as a warm front approaches. Most spray sessions are limited to the early morning hours, say from 4:30 to 9:30, and the evening hours from 5 o'clock until dark. In recent years, Fundy National Park has been in the spray plan. This is a particularly difficult area to spray, not only because of the rugged terrain, but also because, in the early morning, fog and low cloud conditions blanket the area and ground all aircraft. As temperatures increase through the day, the clouds and fog dissipate, but with the rise in temperature comes instability of the air and winds develop. The resulting turbulence then prevents a session from being carried out. In such situations, the sprayers are always standing by to take advantage of the smallest break in the weather pattern so as to treat the area. The spraying program down through the years has never emphasized the killing of bugs, but rather the prevention of massive damage and protection of the trees. We're reasonably sure that with the present methods of spraying, the most modern to this date, trying to annihilate an infestation is virtually impossible. To achieve this goal would certainly necessitate the use of much larger amounts of poison, which is completely unacceptable. However, it's been demonstrated very successfully that trees can be saved at low doses of poison. Unfortunately, the time is limited in which the bug can be sprayed. It's in the 3rd, 4th, and 5th instars that it must be sprayed. There are many and varied reasons why we're unable to work efficiently during the first few instars in the life of the larva. Most of the problem is one of communications. We're unable to get the killer to the victim. In the 3rd, 4th, and 5th instars, the bug has not had a chance to do severe damage, and yet it's in a vulnerable situation with respect to the spray. At this level, we get a high proportion of kill, 80 to 95% of the bugs in the infested area, with the least amount of poison. The time during which the bug is in this stage of development, however, may be very short, 2.5 weeks. What does this spray program do to birds and wildlife? The Canadian Wildlife Service has certified the use of phenitrathion as long as we stay below 6 ounces of active ingredient per acre in any 1 year. We also have the approval of other government departments such as Fisheries, Health and Welfare, the Chemical Control Research Institute, and Forestry at this dosage rate. To date, the dosage used is the best compromise among all the factors involved. It's true that dead birds have been found inside the spray plan. According to the Wildlife Service, this is the exception rather than the rule, and this phenomenon is probably caused by overlaps of spray lines and consequent overdosage. The breakdown time of this emulsion is relatively short compared to the oil solution formulations that are quite stable. Chemists tell us that phenitrathion in bright sunlight breaks down in a matter of a few hours. If the poison is applied within the early hours following its mixing, the effectiveness of the material in the plant tissues may last for several, perhaps 3 weeks, since it's readily absorbed into the plant. Phenitrathion is both a contact and systemic poison, and budworms are killed by the poison landing on them and by the larvae eating contaminated foliage. This has a distinct advantage over strictly contact poisons like DDT. The dosage of poison used in the operation with phenitrathion will not exceed 5 ounces per acre in any 1 year. This is generally enough poison to affect the insect populations, but not to adversely affect other forms of life. The cost of any spray program is determined by many things, some of the more significant being material used, size of the spray plan, dosage rate, average haul distance to the blocks, and the number of applications and method of application used. The project is financed by both the government of New Brunswick and private enterprise. Prior to 1969, the provincial government provided 1/3, the federal government 1/3, and industry 1/3 of the monies needed. However, since 1968, the provincial government of New Brunswick has contributed 2/3 of the cost, and the pulp and paper industry 1/3. In 1971, approximately 6 million acres of the New Brunswick forest were sprayed. The cost was approximately $2,500,000 and was the cheapest project for many years in terms of cost of spraying per acre. However, this cost per acre should only be used when comparing similar large-scale operations, since spraying small acreage would cost much more. It's cheaper by the dozen. Presently, most of the budworm spraying has been carried out in New Brunswick. Smaller areas of northern Ontario and Quebec have been sprayed as well. The budworm is an insect found across North America. In the past 2 years, populations of this insect have increased dramatically, and at present infest 40 million acres in eastern Canada. As a result, Spray operations in Quebec of 2 million acres and in Ontario of 90,000 acres were conducted in 1971. The future will show an increase in the population of this insect, but it's unlikely, unfortunately, that a method more effective than aerial spraying will evolve to control it.